In mathematics, tables of trigonometric functions are useful in a number of areas. Before the existence of pocket calculators, trigonometric tables were essential for navigation, science and engineering. The calculation of mathematical tables was an important area of study, which led to the development of the first mechanical computing devices. Modern computers and pocket calculators now generate trigonometric function values on demand, using special libraries of mathematical code. Often, these libraries use pre-calculated tables internally, and compute the required value by using an appropriate interpolation method. Interpolation of simple lookup tables of trigonometric functions is still used in computer graphics, where only modest accuracy may be required and speed is often paramount. Another important application of trigonometric tables and generation schemes is for fast Fourier transform algorithms, where the same trigonometric function values must be evaluated many times in a given transform, especially in the common case where many transforms of the same size are computed. In this case, calling generic library routines every time is unacceptably slow. One option is to call the library routines once, to build up a table of those trigonometric values that will be needed, but this requires significant memory to store the table. Significant research has been devoted to finding accurate, stable recurrence schemes in order to preserve the accuracy of the FFD. On-demand computation. Modern computers and calculators use a variety of techniques to provide trigonometric function values on demand for arbitrary angles. One common method, especially on higher-end processes with floating-point units, is to combine a polynomial or rational approximation with range reduction and a table lookup. They first look up the closest angle in a small table, and then use the polynomial to compute the correction. Maintaining precision while performing such interpolation is non-trivial, however, and methods like Gall's accurate tables, Codian weight reduction, and Payne and Hannock reduction algorithms can be used for this purpose. On simpler devices that lack a hardware multiplier, there is an algorithm called CORDIC that is more efficient, since it uses only shifts and additions. All of these methods are commonly implemented in hardware for performance reasons. For very high precision calculations, when series expansion convergence becomes too slow, trigonometric functions can be approximated by the arithmetic geometric mean, which itself approximates the trigonometric function by the elliptic integral. Trigonometric functions of angles that are rational multiples of 2 pi are algebraic numbers. The values for a, b 2 pi can be found by applying de Moivre's identity for n equals to a bth root of unity, which is also a root of the polynomial xb1 in the complex plane. For example, the cosine and sine of 2 pi 5/37 are the real and imaginary parts, respectively, of the fifth power of the 37th root of unity cos plus an e, which is a root of the degree 37 polynomial x37 minus 1. For this case, a root-finding algorithm such as Newton's method is much simpler than the arithmetic geometric mean algorithms above while converging at a similar, asymptotic rate. The latter algorithms are required for transcendental trigonometric constants, however, half-angle and angle addition formulas. Historically, the earliest method by which trigonometric tables were computed, and probably the most common until the advent of computers, was to repeatedly apply the half-angle and angle addition trigonometric identities starting from a known value equals 1, cos equals 0. This method was used by the ancient astronomer Ptolemy, who derived them in the Almagest, a treatise on astronomy. In modern form, the identities he derived are stated as follows. A quick, but inaccurate, approximation. A quick, but inaccurate, algorithm for calculating a table of n approximations Sn for sin and Cn for coses. S0 equals 0, C0 equals 1, Sn plus 1 equals Sn plus d times Cn, Cn plus 1 equals Cn minus d times Sn for n equals 0, n minus 1, where d equals 2 pi, n. This is simply the Euler method for integrating the differential equation, with initial conditions S equals 0 and C equals 1, whose analytical solution is S equals sin and C equals cos. Unfortunately, this is not a useful algorithm for generating sine tables because it has a significant error, proportional to 1, n. For example, for n equals 256 the maximum error in the sine values is -0.061. For n equals 1024, the maximum error in the sine values is -0.015, about 4 times smaller. If the sine and cosine values obtained were to be plotted, this algorithm would draw a logarithmic spiral rather than a circle. A better, but still imperfect, recurrence formula. A simple recurrence formula to generate trigonometric tables is based on Euler's formula and the relation. This leads to the following recurrence to compute trigonometric values Sn and Cn as above. C0 equals 1, S0 equals 0, Cn plus 1 equals WR, Cn minus y, Sn plus 1 equals y, Cn plus WR, Sn for n equals 0, n minus 1, where WR equals cos and y equals sin. These two starting trigonometric values are usually computed using existing library functions. This method would produce an exact table in exact arithmetic, but has errors in finite precision floating point arithmetic. In fact, the errors grow so, where epsilon is the floating point precision. A significant improvement is to use the following modification to the above, a trick often used to generate trigonometric values for FFT implementations. C0 equals 1, S0 equals 0, Cn plus 1 equals Cn minus Sn plus 1 equals Sn plus where alpha equals 2 sin 2 and beta equals sin. The errors of this method are much smaller, O on average and O in the worst case. But this is still large enough to substantially degrade the accuracy of FFTs of large sizes.